Okay, this is the 33rd lecture of this course. So, let us first come to the elementary fact about polynomials, which I got stuck where I got stuck yesterday. So, it is an elementary thing. As I said, the proof is just the imitation of the proof for integers, but somehow the trick was not clicking. But after the lecture, what happens usually mostly that it suddenly clicks. So, anyway, so let me do it first. So, the statement was, suppose f and g both divides h, all of these are polynomials in single variable, and GCD of f comma g is f and g is 1, then f g divides h. That is actually easy to prove. In fact, I was almost on the track, but then somehow missed the main point. So, you can write f as 1 as a linear combination of g and f. Okay. Now, what you do is you multiply both sides by h, f h f 1 g h g 1 equal to h, and then since h is a g divides h, so you can write, let us say if h equal to g times something f 1. Similarly, here you can write f times again something equals to this. Now, you see you can take f g common, that shows f g divides h. Anyway, it is a trivial one. I mean, I wrote that this in the last lecture, but then somehow forgot to notice that, somehow missed that here h also can be written f times something or j times something interchangeably. Anyway, so I think I thought that since I got stuck, it is my duty to do that here. Now, let us come to the main topic of this lecture. So, recall that what we were doing is the following, that our job was to so given a linear operator on a finite dimensional vector space, we undertake the theme of bringing the matrix, we undertake the theme of finding a suitable ordered basis such that the matrix of the linear transformation linear operator takes the simplest form, say, takes this possibly simplest form. So, we have agreed that if we can bring it to the diagonal form, then then we are in a very good shape. So, then in that case we say the operator T is diagonalizable, and we have proved the four equivalent criterion for that. One was T is diagonalizable, the other one was it has an eigenbasis. The third was V can be decomposed into the direct sum of the eigenspaces, where lambda runs over all eigenvalues of T, and then finally the minimal polynomial of T, it is of this form. Okay. So, where lambda I are not equal to lambda j. Okay. So, again like we regarded that the diagonal form is the simplest form which you can expect a large class of matrices to we believe that the large class of linear operators we can reduce their matrices to that. Okay. We indeed this is the case, that is a sufficient, the class of such operators, diagonalizable operators, is actually quite large. Later on we will prove, if time permits, some density statements which says that for a complex for example invertible matrix, they can be approximated by diagonalizable matrices. Anyway, so these are the, so the point of all these is just to convince you that the class of operators for which a class of diagonalizable operators that class is sufficiently large, but however, there do exist linear maps, linear operators which are not diagonalizable. We have already seen one example. So, for them what can happen them for them their minimal polynomial can and the following can happen with the minimal polynomial of for such operators. So, one thing that can happen that so here what is the case? Here the thing is all irreducible factors of the polynomials are linear factors. Let me recall some basic facts for polynomials is that if you remember that every positive integer can be written as a product of primes. So, similarly every non-zero polynomial can be written as a product of let us say irreducibles q1 up to qk and this factorization is unique up to rearrangement of the terms. Okay. So, this we will call the irreducible factors of f, and how do you prove the existence of such thing? That proof is also goes almost along the same line of with that of for integers. So, if f is irreducible we are done, otherwise f will have factors. So, we will take the least degree factor, okay, least degree non constant factor. So, then when we divide f by that factor, then the polynomial will have degree less than that of f, then you run a typical induction argument. So, therefore, that is how we prove. So, this is exactly the same proof that for fundamental theorem of arithmetic, right, the same proof goes in the same technique. So, now let us come to here. So, the following can happen to MT for which suppose T is not diagonalizable, the following can happen to the minimal polynomial of MT polynomial of T, that either it might have a irreducible factor having degree at least 2. Okay. So, for example, let me give you this example of let us say rotation in the anti-clockwise direction with 90 degree. So, the matrix looks like, so E1 goes to E2 and E2 goes to minus E1. So, A square equal becomes minus identity, therefore, the minimal polynomial. So, if we regard over R, so this is irreducible, it cannot have a linear factor in over R, right. So, certainly this is not going to be diagonal. So, this map as a map from R2 to R2, this rotation map is not diagonal, or this or linear operator is not diagonalizable, right. So, yeah. So, it can have factors, irreducible factors having degree at least 2, or even if it has all irreducible factors linear, still there could be repeated roots. Okay. For example, we will see that let us say let us look at the following that so we wish to have a repeated root here, therefore, this is a better way of doing that 0 0 1 0. Okay. So, if this is A, regard A as a linear operator from R2 to R2, or even if you regard this over C2 just to make sure that all irreducible factors, what I am saying that even then if you want to make sure that all irreducible factors are linear, even then over C, so A square is 0, right. So, therefore, this is the minimal polynomial of this linear operator. Okay. So, certainly this is not diagonalizable. In fact, a similar such thing we have seen in the last lecture. So, as I said, there are two kinds of problems. First of all, it may have a irreducible factor of irreducible factor of degree at least 2, or even if all the irreducible factors have degree 1, still there could be repeated roots like this. So, in such cases we cannot expect them to be certainly these are not going to be diagonalizable. So, the question is, since they are not diagonalizable, so we cannot bring their matrices into diagonal form, then the natural question is, can we think of the some other simplest form, maybe one step maybe one step beyond as I said in the simplest form of matrices, such that their matrices can be brought into this form. I repeat, so for example, try to see. So, though this is not diagonalizable, however, if you look at his matrix, we should it seems quite acceptable to us, right, because it has only 1 1 and the rest 0. So, therefore, even if our primary aim was to bring the matrix in the simplest form. So, even so what is the operator here? Operator is A E1 equal to 0 and A E2 equal to E1, or more generally A of x comma y, x1 E1. So, yeah, y E1, y comma 0, right, y comma 0. So, even if this linear operator is not diagonalizable, still its matrix we can see it is in a form which we may regard as which we may accept as the simple. So, the question is the following, that if for an operator, for the operators which are not diagonalizable, that is their matrices cannot be reduced to a diagonal matrix, for them what kind of simplest form we can think of reducing their matrices to. Okay. For if diagonalizable, of course, again let me repeat that earlier we thought that earlier we took we have our aim was to bring the matrix into the diagonal form, bring the diagonal form, because that we accept that as a simplest form, and simplest form is not absurdly simple as well. So, but we do have operators for which is not diagonalizable, then what kind of simplest form that we can think beyond the diagonal form. So, try to see the following, that if the matrix is, so let us try to observe what is going on. If the matrix is not in the cannot be in a diagonal form, and suppose let us say we can have this, let us say 0 1 0 0, and then we have let us say 1 1 0 0, and then again 0 1 0 0, and elsewhere 0. Even this one should be acceptable, because here also it has mostly we have zeros, and other than that only a few elements are there which are not actually creating so much trouble, so that when we make computations things will not be too complicated. So, this kind of things, like which is in a sense the extension of this. So, they are such kind of matrices we should, what I am saying is we should broaden our horizon of acceptance, and it is reasonable to accept these matrices as well. So, how are these matrices, how does such a matrix look? So, you see, first we have this, then we have here an identity block, and then here we have again this, and rest are 0. So, basically we are, so for the matrices which cannot be brought into a diagonal form, we can, the best we can expect them to be reduced to is block diagonal form. So, it will be a matrix, it will be a block diagonal form means, so along the diagonal several block matrices are placed and 0 elsewhere. So, for example, this is one example. Okay. So, the size of the block can be anything. In particular, we see that this generalizes the diagonal forms, diagonal matrices where all the blocks are having size 1. Okay. So, along the diagonal several square block matrices are placed and 0 elsewhere. Okay. So, now we have at least convinced ourselves that for more general linear operators for more general linear operators beyond the diagonalizable ones, this is we may try we may expect, or we can at least try to bring their matrices to such a form, right. Okay. So, let us see if what it means. For example, we see that if some matrix can be brought into, if the linear operators matrix can be brought into diagonal form, then that gives me some decomposition, right, namely the decomposition into eigenspaces. So, let us see here what we can say. So, if we have a block diagonal form, so remember, so what let us assume that the size of A1 is, let us say, n1 cross n1, size of A2 is n2 cross n2, and size of A, well, I should write k should be nk cross nk, and if n is the dimension of V, then we must have n1 plus up to nk is V. Okay. Now, remember, this is the matrix of the linear map T with respect to the same ordered basis, right, same ordered basis B. So, therefore, suppose first n1 vectors of B are the following: V11 up to V1 n1, then the second n2 number of vectors V21 up to V2 n2, and similarly Vk1 up to Vk nk. Okay. So, let this be our whole B. Okay. So, if this is so, then what can we see? So, I mean, call this is as B1, B2 and Bk, and define Wi as the linear span of Bi for each I. Then we find that each Wi is invariant, right. Try to see, I mean, what I am trying to observe is, if the matrix can be brought into the block diagonal form, then each Wi has to be invariant. Why? Because a typical member in Wi will be just a combination of V11 up to V1 n1. Once I apply T on them, it shows that V1. So, try to see. So, T V1, when I write T V1 as a combination of these of the basis elements in B, then you see the all coefficients of V21 up to V2n2, and then going further, all the coefficients of these vectors will vanish, right, for V1, T V11, similarly for T Vn2. So, for any I, once I write T Vij, where j runs from 1 up to ni, so there what I will have is the coefficients of all T, the coefficients of all vectors, coefficients of V I prime j's for any other I prime, for any other I prime, then I, all the coefficients will vanish. That is what we can see from the block diagonal form, that I mean, at more for let us say for A1, try to see for A1 only coefficient in the matrix A1. So, let us say in the first column, at I mean the entries beyond n1 plus 1, all of them have to be 0, right. So, therefore, T V1 and the coefficients of T non-zero coefficients can go only up to the n1 place. That means, the coefficients of only these vectors can be 0, at most rest will be 0. So, that actually holds for any I, that is what this diagonal form shows. So, therefore, all these are invariant, and since we have made this is a partition of the basis B, we easily get V equal to the direct sum of W1 up to Wk. Okay. So, therefore, what we have seen is, if we can bring the matrix into a block diagonal form by choosing an ordered basis, then that is leading me to a decomposition of V into invariant subspaces, right. Now, look at the converse. Suppose I have obtained that suppose given T, I have obtained W1 up to Wk such that each of them invariant subspace, invariant under T, and V is W1 up to Wk, then what do you do is we pick up an ordered basis of we start with an ordered basis of W1, okay. Then with that we will, I mean, for each, well, what we do is for each I we choose an ordered basis, let us say V1 up to Vi Ni, where Ni is the dimension of Wi, ordered basis of Wi, and then we finally define the ordered basis B to be the union of, and assume that they are ordered in they are ordered according to the arrangement that the first n1 vectors are the n1 vectors of B1, and then the next n2 vectors are the n2 vectors of B2 in their original order. So, then B will be an ordered basis, then B is an ordered basis of V, because once we have a decomposition, then taking basis from each of the summand and having their union, that you will have a basis of V. And now with respect to this basis, when you write down the matrix of T, then it is very easy to see what is happening is, let us say if I start with the first vector T V11. So, since Wi is let us say start with W1, whatever happens with 1, then you see that there is nothing wholly about 1, that goes for any I. So, for simplicity, let us work with W1. Once you, as I said, once you understand what happens with W1, then you will be immediately convinced that that goes for any I, there is nothing wholly. So, if you start with the first vector of W1, first basis vector, let us say V11, then since Wi is invariant, so TV1 will be TV11 will be inside WV1, and since the sum is direct, it cannot it cannot lie inside any other Wj unless this is 0. So, you see in either case only TV11, when it will be written as a linear combination of basis elements here, you see only these vectors can have non-zero coefficients, the others cannot have, because of the sum is direct, okay. Because TV11, try to understand, TV11 is lies inside W1. So, therefore, TV11 can be written as a linear combination of V11 up to V1N1, okay. So, therefore, writing TV11 as a linear combination of the ordered basis of B is nothing but this together with the other vectors coming from other BI's with 0 coefficients. So, therefore, the first column will be only first nith coefficients can be non-zero, then rest of them have to be 0. Similarly, for TVI2, you can see only the first n1 coefficients are allowed to be non-zero, at most rest will be 0. So, therefore, we see for that, at least for the first n1 vectors, the first n1 columns will look like this, okay. And then if you look at the second n2 vectors, then you see their coefficients. So, only V21 up to V2 and V2N2, their coefficients are allowed to be 0. The coefficients of, let us say, V1 up to Vn1, they have to be 0, and similarly for V31 or the rest. So, therefore, the next n2 columns will look like as follows, that only here you can have non-zero elements, but rest have to be 0, and similarly this goes on, okay. So, what we have seen is, if we have a decomposition of V into invariant subspaces, then the matrix can be brought, then the matrix by choosing ordered basis from each of these summands and taking this union, then when we write down the matrix for that operator with this ordered basis, the matrix will be a block diagonal matrix. So, this, in view of this and this, we are now convinced that bringing the bringing the matrix of a linear transformation into the block diagonal form is equivalent to decomposing the vector, the whole vector space V into T invariant subspaces, okay, into T invariant subspaces. Try to remember earlier when T was diagonalizable. So, as Wi I got as these Wi's we got the eigenspaces, and since there each vector is being mapped to its mapped to a scalar multiple of itself. So, only the diagonal elements are allowed to be non-zero and nothing else. So, even then it might be in each block the diagonal elements are non-zero and nothing else, therefore, the entire matrix becomes diagonal. That is what we have seen there, but here in addition to the diagonal elements, for example, in the first in this block, there is no there is no reason that only diagonal elements will be non-zero. There could be other non-zero elements, but at least one thing is clear that other vectors, let us say, which are the other vectors, like, well, not other vectors, the other coefficients apart from, let us say, for W1, the other coefficients of other V I prime j's, where I prime is greater not equal to I, other coefficients must be 0. Okay. So, now we have convinced that why these are why this situation is more general than that of diagonalizable operators, because for diagonalizable operators this is what was happening with something extra, but in general there is no need that it will happen. At most we can say that the non-zero entries can lie in the blocks, block matrix in the blocks along the principal diagonal. Yeah, try to understand, for diagonalizable case, apart from the diagonal rest were 0, in general we do not have that privilege, but at least we have this much of privilege that the apart from some coefficients, let us say here apart from only these n1 square number of coefficients, then the rest which comes below has to be 0. Similarly, for here, apart from these coefficients, the what lies on the top and what lies below, all the entries are to be 0, right. At least this much we have, and we cannot we cannot it is not reasonable to expect anything beyond that. Okay, fine. So, therefore, bringing into block diagonal form is now decomposing V into invariant subspaces. Okay. Now, let us come to this point. So, therefore, given W, I will in order to bring its matrix into a block diagonal form, we would therefore strive to get a decomposition for V. Okay. Now, I am telling you that we do have a decomposition for V, but that may not be but we cannot stop with that. Let me just explain. So, we have the minimal polynomial for T, right. So, what is the minimal polynomial for T? So, let this be the minimal polynomial for T. Let us say P1t up to Pkt, these are the irreducible factors. And Pi n not equal to Pj for all I not equal to j. Okay. So, I should rather put like this. So, well, so it is not quite, it is not for a general polynomial we cannot expect this to happen. There is just the product of the irreducible factors, and each irreducible factor occurs once. So, we should there should be multiplicities of each of these irreducible factors, but then what we will do is we will relabel P1 to the power alpha 1 by P1 itself, and instead of then asking insisting P1 is irreducible, we will rather simply, so basically what are PIs? PIs are the products of the same irreducible factors. So, we should instead that P instead insist that for I not equal to j. Okay. Since P1 is P1 is the the product of all same irreducible factors of one kind. So, from a Pi and Pj there cannot be any common factor. Okay. So, this is what we have, and then kernel of MT is going to be V, right. Kernel, so then this is a kernel of P1T kernel of PKT. Okay. So, yeah, therefore, thus given a linear operator, we do have a decomposition of V into invariant subspaces, okay, and we do have a linear invariant subspaces. Remember, these can be empty as well. One of them, this can be trivial as well. For example, if my operator is invertible, and if my operator is invertible and it has a factor like this, okay. So, well, so just a minute, yeah. So, what I am saying is, yeah. So, this can be in general some of this can be trivial as well. So, you can construct examples for that. I should, since I do not have much time. So, I leave this exercise to you to find such an example, and instead I will go ahead. So, now come to the point that we do have a decomposition of V into invariant subspaces, and thus given any linear operator I can decompose that into a block diagonal form, okay. Fine. Now, the issue, therefore, apart from the diagonal ones, everything else has been in a sense ruled out. Now, what we should expect that, because but inside the diagonal ones, inside this the blocks which are appearing here, the blocks, like, try to understand. So, at least we have assured that the elements which are beyond which are not lying in any of these blocks, they will be 0, but the elements, but not the elements, the entries which are in those blocks, some of these entries or many of them, whatever, but the entries here in the blocks can be complicated. So, therefore, though we have a decomposition, it is not a wise decision to stop with that. We should rather strive to bring the elements in these blocks in the simplest form as well. Again, what I mean by that is, I will try to make as many elements, I will try to bring as many elements 0, bring as many elements to 0 as possible, and those who are non-zero, I have to I will also try to make them 0. I will also try to make them into something maybe reasonably simpler. Okay, so I should go ahead. Therefore, now my job is to, so given a linear operator, I will write its minimal polynomial and factorize it as follows, and then we get this decomposition. So, therefore, what I will do now is, I will try to choose an appropriate ordered basis for each of these kernel PIs. so that the kernel PI, so that this ith block becomes simpler. Okay. Simpler means in the sense that I have already talked about. Okay. So, remember somewhat our motivating factor was to bring bring matrices of this form. So, what are the, I mean, if you look at let us say if I can have this you can have such a matrix in the block, then we will accept that, well, it is simple, it is in a form that we should accept. Now, therefore, let us try to explore what these matrices are. So, 0 0 1 0, if I just consider the linear operator given by this matrix, we see that. So, A E1 is 0, if I call it A E1 is 0, then A square A E2 is E1, then further applying A square E1 E2 is also 0. So, therefore, A square E1 and A square E2 both are 0, therefore, A square is the null matrix, right. So, A compose A, which you write by A square is 0. So, therefore, these matrices, so this is not the now I mean in general operators for which, so let us make a definition. So, let T is linear. So, these linears have a general name in the literature, is called nilpotent if there exists k and such that t to the power k is 0. That is, composing k, composing t with itself for k times, it will give you the 0 operator. So, what are the let me give you a few examples. So, an example of a nilpotent, so null matrix null operator is already a nilpotent operator. So, this operator that I have talked about, this is a nilpotent operator, and you see we can further generalize. So, what was happening was, if you look at the matrix, so each vector, so what is this what is this matrix actually, what kind of matrix is this? Not, it is upper triangular, not only upper triangular, we have something more, that is strictly upper triangular in the sense that diagonal entries are also 0. So, therefore, we can expect this to happen in the generality. It is reasonable to expect that operators whose let me put it in this way, that if t can be brought well, I should not say t, rather the matrix of t. So, what I want to formulate is if, well, I think there is a better way is, if there is an ordered basis B such that the matrix of T is strictly upper triangular, then T is nilpotent. Okay. So, as I said while giving examples, the reason for generalizing it, that actually captures a large class of examples. So, basically I have though with the intention of giving an example, what I have stated is more like a general result. So, we have to prove this. So, Its proof of this is very easy. So, suppose B is the ordered basis V is V1, V2, Vk. Now, since the matrix is strictly upper triangular, then what happens to TV1? So, the matrix is strictly upper triangular. So, diagonal elements are to be 0. So, TV1 has to be 0. Then what happens to TV2? TV2, what are the when you write that as a linear combination of VI's, you see I mean diagonals are 0 and anything below diagonals they are also 0. So, therefore, only non-zero coefficient can appear here. So, TV1 must be some, TV2 must be some linear combination of V1, and then you see that for any TVI, so these coefficients beyond the ith row in that the entries must be 0. So, therefore, TVI can be written as a linear combination of, so even ith diagonal entry has to be 0, linear combination of the previous vectors. For example, Vi2, Vi plus 1, Vi minus 1, Vi minus 1, right? Rest of them have to be 0 because the matrix is in the strictly upper triangular form. And now that is very easy. So, this vector vanishes when you apply T once, this vector vanishes if you apply T twice, because T square V2 will be T V1 times some scalar, it will be 0. So, therefore, in general the vector Vi gets annihilated once you apply Ti times, right. So, therefore, T to the power n vanishes, I mean yeah, for if this is Vn, n is the dimension, then T to the power n kills all the vector basis vectors, hence the T to the power n, that operator will be 0. Okay. So, therefore, we know that how to how to generate a nilpotent operator, namely we have to start with a strictly upper triangular matrix, and then that gives me a nilpotent, the corresponding operator is a nilpotent operator. Okay. And also this shows us that not only, so what you have to do is, I mean this shows also something that because if this results talks about if there is an ordered basis. So, it also tells you that if you start with a strictly upper triangular matrix, then conjugate that by any invertible matrix P, and then the conjugated matrix may not be a strictly upper triangular any longer, but the corresponding linear operator from let us say Cn to Cn or Rn to or Fn to Fn, they must that operator must be nilpotent. Okay. Yeah. Surprisingly, its converse is also true, that if an operator is nilpotent, then if an operator is nilpotent, then there is a basis, ordered basis, for which the matrix becomes a strictly upper triangular matrix. We will prove that. Before that, we need to talk about something, then we will prove that. So, yeah. So, then the natural question is why I am talking about nilpotent operators. As I said that I was as we can see that we are motivated by some examples, but I mean it is very legitimate to say that is that example very very special, that is I mean that is yeah operators for which we can have something related to something connected to nilpotent ones along the diagonals. I mean are such operators very special? If very very special and the class is very very small, then I mean their study does not give us much, okay, because as I say our always the point of general study is we want to touch upon a broader class as much as we can. So, now I will convince you that indeed this is the case for I mean for C, well let me talk about C, then I will put the general statement. If the vector space is over C, then we do have something which is intimately connected to the nilpotent ones along each blocks. So, I think it is better if I be more formal and tell you in an organized and formal way. So, yeah, so let us assume that MT the irreducible factors well, so assume that MT splits over F. So, what I mean by splitting over F is all the irreducible factors are linear factors. There can be repeated factors, like let us say x minus lambda might have multiplicity, let us say something m, but the only point is it does not have any quadratic or irreducible polynomial of higher degree or an irreducible factor of higher degree. Okay. So, then this is what we call as the it splits over F. So, therefore, if MT splits over F, then the minimal polynomial of T has the following form. Okay. Now, therefore, under this assumption, V is nothing but kernel of, we see that kernel of Mi direct sum 1 up to k. All right. Remember, unless we assume that this Pi, some of these Pi's or maybe all of them might have a factor, of degree might have a factor of higher degree. Okay. And also one thing, as I said, that if let us say if I consider the over, let us say over R, because over C automatically every polynomial splits. So, over R if we take the rotation 90 degree angle, that rotation to the 90 degree rotation with an angle of 90 degree in the anticlockwise direction, then its minimal polynomial will be t square plus 1, right. So, it is itself an irreducible polynomial and it has no linear factor. Okay. Yeah, let us come here. So, now let us for that so now let us try to see each of these summands. So, a typical, so again the question can be that I mean the very natural question is whether this can be empty or this can be trivial or not. Okay. But this in this situation this will not be trivial, because because since these are the roots of minimal polynomials. So, lambda I has to be a eigenvalue, therefore, there is a non-zero vector. Therefore, now they have a non-zero vector V such that this is 0, and then when I apply the operator on this will be certainly 0. So, therefore, it shows that all these are always non-trivial. Okay. Now, the more important thing is, let us try to observe that if I have a vector here V, then then according to its definition t minus lambda I to the power mi for any vector irrespective of 0 or non-zero becomes 0. Okay. It becomes 0. So, that means t minus lambda I on, so these are all invariant, these are all T invariant subspaces, right. All these we have already seen. The kernel of any polynomial kernel of Pt is always T invariant. So, this if look at this invariant subspace, non-trivial invariant subspace. So, on this operator is nilpotent. Okay. So, this is what I was saying, that under this assumption, well, if I take f is c, then I do not need to put this assumption, this automatically there. So, to be simple, if I to talk about in simple terms, for any linear operator on complex vector spaces, we naturally we do have nilpotent operators on the let us say on the direct summands of this decomposition of V. Okay. So, now we have to observe that this operator T minus lambda I is, as I said, this is nilpotent. T minus lambda I as a map, if for the time being I call it Wi. So, is a map from Wi linear operator on Wi, this is nilpotent. So, suppose if suppose that I can bring, I have a general method to bring the matrix of a nilpotent operator into the simplest form, which is at which all of us can accept, then the matrix of the linear operator T will be just nothing but the matrix of this nilpotent operator together with this diagonal matrix whose all diagonal entries are lambda I. Try to understand. So, the matrix of, so what I am saying is, suppose I can choose an appropriate basis B such that I can make this the matrix of this operator a simple one. A simple means we are ready to accept that. Then from that matrix it is easy to get the matrix of the linear operator T on restricted to Wi. What is that? This is nothing but the matrix of this together with the diagonal matrix whose all diagonal entries are lambda. Okay. Therefore, this shows that if we can have a general method of reducing the matrix of a nilpotent operator to a simplest one, then our purpose will be served. Okay. So, that shows us we should rather look for we should now look for the methods to bring the matrices of nilpotent operators into simplest forms, okay, because they do appear very naturally in this decomposition. Okay. So, at this point of time I will make a general definition, and then I will get back to nilpotent operators. So, because these are very natural to make here. Okay. Yeah. I think I have made a small mistake. I think let me correct that. So, earlier as I said that yeah, I think I made the mistake. Suppose P1, P2, Pkt is the factorization of the minimal polynomial with where each Pi is the product of the same irreducible polynomials. Yeah. Then I said that some of the kernel of this Pk might be trivial, but that is not the case, because this is actually the minimal polynomial. Let me tell you why. Because let us say Pi, so we take the product of other Pj's, yeah, P1, P2, Pi minus, so take the product of other Pj's. Okay. So, this is a polynomial whose degree is less than that of the minimal polynomial. So, therefore, P1t compose Pi minus 1t compose Pi plus 1t Pkt. This is not going to be identically 0, right, because it is a minimal polynomial. Hence, there will be a non-zero vector, so for which this is non-zero, right. This is non-zero, and yeah, now when I apply Pit on this non-zero vector, I will have 0. So, therefore, this whole vector lies in the kernel of Pit. So, if these are the so none of these Pi's can have trivial, and none of them can have trivial kernel. Okay. So, here from here it we can use this general phenomenon to this context as well, and here I mean of course we proved it separately, and yeah of course we proved it separately, but we see that actually that is not needed, right, that is not needed, but anyway we have a separate proof for the special case as well. Okay. So, now let us go ahead. What was I yeah. So, I think this lecture I should stop this lecture soon, because I am the time is already over. So, let me see whether what should I finish here, or I should say something. I was talking about the this nilpotent ones. Yeah, okay, I will make a definition, and then with that I will finish. Okay. So, as I said, look at a vector here, let us say V, any vector lying in the kernel of this operator. So, that vector, I take a non-zero vector, that vector may not be an eigenvector, right, because t minus lambda I times v may not be 0, because what at most I know that t minus lambda I times m I, when that applies to v, this is 0. So, the vector may not be an eigenvector, but however it is in a sense somewhat generalized than that of eigenvectors, because the first power of this operator may not kill this, but somehow there is some higher power or some other power will kill it. So, that motivates us to the so this phenomenon we record as a record in terms of record in a general definition. So, given t is linear, and alpha is a scalar, then yeah, a vector, these are given, a non-zero vector, non-zero is said to be a generalized eigenvector, corresponding to lambda if t minus lambda v is 0 for some positive integer k. So, the definition is, as I said, I am motivated. So, what I have seen here, this is what I am making, this is what I am putting it in a general definition. So, I will say a vector is a generalized eigenvector, generalized in the sense that for the eigenvector corresponding to lambda, that operator t minus lambda was directly killing that vector. So, I am somewhat relaxing, I am somewhat generalizing my notions. Well, I have to justify why I am saying it is generalized, but what I am doing is I am allowing not only the vectors which are killed by t minus lambda, I am allowing all the vectors which are killed by any powers of all the vectors which can be killed by any power of this operator. So, such vectors so such a vector, non-zero vector of course, which is killed by a power of t minus lambda by a power of this operator, then we call such a vector as a generalized eigenvector. In the next lecture I will give I will continue with that. So, with that I am finishing this lecture. Thank you.